This section should be review of college algebra. You should have seen this stuff somewhere in your past. This is polynomial functions and models. So the first objective here is to be able to identify a polynomial function and their degrees. Polynomial functions are a function in this form. A here represents a constant, they're real numbers, and n is a non-negative integer. Integers are the numbers that you learned in kindergarten. Those are the 1, 2, 3, so forth and so on. The domain is all real numbers. The domain, remember, is the value that goes with the x's on a polynomial function. This is what a polynomial function looks like. The degree would be the highest power of an exponent on the variable x. X is the only variable here. Remember, this is function notation. This is read f of x equals, not f times x. Let's look at this first example problem. We're asked to identify a polynomial function. We want to identify whether or not the following are polynomial functions, and then for the ones that are polynomial functions, state the degree. For those that are not polynomial functions, I want you to be able to tell me why it's not a polynomial. Starting here with problem A. F of x equals 3x minus 4x cubed plus x to the 8th. Is this a polynomial function? Yes, it is. What is the degree? It's the highest power of the x. Is B a polynomial function? Do you see any fractions up here? This is actually raised to a power of -1. So this is a rational function, not a polynomial. What about C? Is this a polynomial function? Oddly enough, this is a yes. The degree here is, because we could stick a term on here, 5 times x to the 0, because remember, anything raised to a power of 0 is 1, and 5 times 1 is 5. So we would say that the power here is 0, so the degree is 0. A constant actually is a polynomial function. D, f of x equals x minus 3 times x plus 2. Is this a polynomial function? Yes, it is. It just doesn't look like all of the others did because it's a factored polynomial function. So this is a yes. And what is the degree going to be then? 2. Because when we FOIL this out, we would actually get f of x equals x squared minus x minus 6. How about E? G of x equals 3x minus 4x to the -1. Why not? The negative exponents. Do y'all remember your properties of exponents, what a negative exponent does? In order to make a negative exponent positive, let's recall, if we have anything raised to a negative exponent, we can make that negative exponent positive by moving that term into the denominator. So E actually is a not so obvious form of a rational function. And then F. Is F a polynomial function? Yes, it is. And what is the degree? Nothing says the coefficients in front of the variables cannot be fractions. It's just that the variable cannot be in the denominator. Let's check your vocabulary. Do you remember what leading coefficient means? What would be the leading coefficient of F? 1/2. Polynomial function will always be smooth and continuous. As long as a function fits the conditions of being a polynomial, the graph will be smooth and continuous. So this graph right here would represent a polynomial function, whereas this one would not. And there's several reasons why this cannot be a polynomial function. The first one is we have a corner. You see that sharp angle there? That's a corner, and a corner is not smooth. There's a cusp. Once again, it's a pointy part of a graph. A cusp is not smooth. That violates the conditions of being smooth. And then here we see a gap in the graph as well as a hole, and these violate the conditions of being continuous. The graph of any polynomial function will be smooth and continuous, and the domain will be all real numbers. Next, we're going to talk about power functions. A power function of degree n is a function of the form f of x equals a constant times x raised to a power. A can be any real number, positive or negative. It just cannot be 0. And your exponent here cannot be negative. This has to be a polynomial function. It has to fit the criteria of a polynomial function. For example, here's a power function of degree 1. The constant is 3. Here's a power function of degree 2. The constant is -5, so forth and so on. This happens to be a linear function. Its graph would look like a line. Quadratics have this general shape, either opening up or down. Cubics have this general shape. X to the fourth, it's kind of like the quadratic. It just gets a little flatter and wider here for the power function. But if you look here, here's a picture. In black, we see the quadratic function. In blue, we see the quartic function or the fourth degree function. The base of it there at the vertex is just a little wider for the fourth power. Here's the properties then of a power function if the power is even, a positive even function. If f is even, the graph is symmetric with respect to the y-axis. Do y'all remember seeing those words going together at some point in your past? Even, symmetry with respect to the y-axis. The domain is all real numbers. The range is a set of non-negative real numbers. The graph always contains these points. The vertex will be at 0, 0 because there's no horizontal or vertical shift. -1 raised to an even power will always be 1. 1 raised to an even power will always be 1. So these 3 points right here are guaranteed to be on the graph of any power function that's raised to an even power. As the exponent increases in magnitude, the function increases more rapidly when x is less than -1 or bigger than 1. So what it means is these lines here will go more vertical. If we looked at x to the 6th, these lines would be more vertical and it would flatten out a little bit more if we had x to the 6th. Here's properties of power functions if we have x raised to an odd power. If f is an odd function, we say this is symmetric with respect to the origin. At some point, hopefully somebody told you all of the O's go together. Odd, origin, opposite. To check and see if a function is odd, on an odd function, f of -x would be the opposite of f of x. So if you have an odd function and the leading coefficient is positive, it's going to be an increasing function. The ends will point in opposite directions. In an even function, the ends pointed in the same direction, both going up or both going down. But in an odd function, the ends go in opposite directions. So what we could say here is, given f of x equals a times x to the n, if a is greater than 0, the graph will open up like this, the ends going in the same direction, opening up. If a is negative, this graph will be pointing down. And you can tell if a function's even by replacing -x with x, and you get the same function back. If we're given g of x equals a x to the n, where n is odd, if a is greater than 0, this is going to be an increasing function. If a is less than 0, the shape will be a decreasing function. Increasing means going up as you move from left to right. Decreasing means going down as you move from left to right. Now, all of this becomes really important whenever we look at graphing polynomial functions using transformations. I'm going to summarize all of that for you. The horizontal shift is inside the function, and it moves opposite the sign. By that I mean that a plus is going to go to the left and a minus is going to go then to the right. K here is a vertical shift. It's found outside the parent function and it moves with the sign. So a plus is going to go up and a minus is going to go down. In this next example, we're asked to graph the polynomial functions just using transformations. Our parent function here is going to be a quintic. In this quintic, there's a -1 in front of our parent function. What does this negative right here do? It flips this. So we would start out with a function raised to an odd power. That's where we get this same basic shape from. The points -1, -1, 0, 0, and 1, 1 are our reference points. Those points are going to be included. But when we flip this across the x-axis, we see that these points now are reflected about. So we have the point -1, 1, 0, 0, and 1, -1. So this is our reflection. And then what does this 1 right here do? No, it doesn't stretch because it's not multiplied by the x to the 5th. It's a vertical shift, and it's going up 1 because that 1 is positive. The negative here was for the reflection. So a negative would reflect this about the x-axis. Start with your parent function, flip it, and then slide each of these points up. So this point right here, negative 1, 1, got moved to negative 1, 2. The point at 0, 0 shifted up 1 to 0, 1. We're just sliding everything up 1, and that's how we got to this graph right here. This is an equal sign, not a minus. That just didn't come out real well. This equals 1/2 x minus 1 to the 4th. What is your parent function? That's probably the first thing you want to do is identify the parent function. So this is a power function. Are the ends going to be going the same direction or opposite directions? Same direction. Up or down? So our parent function has this basic shape. And what points are we guaranteed are going to be on this graph? 0, 0, 1, 1, and negative 1, 1. That 1/2 do next? It compresses everything by a half. So that means that this point at 0, 0 is still going to be at 0, 0, but what happens to the point at 1, 1? It becomes 1, 1/2. So what we see then is this shape right here, where these points are at 0, 0, 1, 1/2, and negative 1, 1/2. And then the third thing is the horizontal shift, and our horizontal shift is going to go what direction? So that's what we did then and end up with these points. So we take this point and shift it to the right one, and that gives us 0, 1/2. The next thing we want to do is be able to identify the real zeros of a polynomial function along with their multiplicity. The multiplicity basically is just going to be the power on the root. Root is also known as zeros. It's also known as x-intercepts. It's also known as factors. Here, notice we're crossing the x-axis. If the graph crosses the x-axis, then we would say that this root has a multiplicity that is odd. If the graph ever just comes up, touches the x-axis, and goes back down, then the multiplicity is even. It does like a bounce back. So if the graph crosses, we know the power is odd. If it touches and comes back, we know that the power is even. Definition: if f is a function and r is a real number for which f of r is equal to 0, then r is called a real zero of f. As a consequence, the following statements are all equivalent. R is a real zero, it's an x-intercept, it's a factor, it's a solution of the equation. All of these things are synonymous, and you will hear, depending on the instructor and the course and the author of the book that you're using, you will hear them called all of these things at different times. A large part of learning mathematics, I think, is learning our terminology, our jargon that we use, and this is part of it. Factors, zeros, x-intercepts, they all mean the same. Example, finding a polynomial function from its zeros. Find a polynomial of degree 3 whose zeros are negative 4, negative 2, and 3. Based on what we just read, what does this mean if I were to write this out in function notation? It means I could write this as f of x equals x plus 4 times. That's another way of writing this out. We could be off by a constant if there were a stretch there. And if they told us a y-intercept, we could actually plug in a 0 for x and a number for f of x for our y-intercept and solve this for a. We have a graphing calculator. We can multiply this out. This would give us f of x is equal to, let's FOIL out the first two terms. That would give us x squared plus 6x plus 8, and we multiply this times x minus 3, and that would give us x to the third. And then that's 6x squared minus 3x squared is 3x squared. 8x minus 18x would be minus 10x, and then last would give us minus 24. So it looks like this is what we could graph, and we would see that the graph then would actually cross the x-axis at these points. If x minus r raised to the m is a factor of the polynomial, and x minus r raised to the m plus 1 is not a factor, then r is called a zero of multiplicity m. So for example, x right here would be a 0 of multiplicity 1, but 3 would be a 0 of multiplicity 2. So find the x and y intercepts of the graph. Do you remember how to find your x-intercepts? You set this equal to 0. So to find your x-intercepts, we would solve x times x minus 3 squared equals 0. And then to find your y-intercepts, we're going to solve f of 0. We just plug in a 0 for x and solve for y. So for A, we want to find our x-intercepts first. We find that by setting the factors x times x minus 3 squared equal to 0. This, thanks to the zero product rule, is going to be true as long as either x is equal to 0 or x minus 3 squared is equal to 0. There's a solution, x equals 0, and this one is going to be true as long as x is equal to 3. Don't worry about the square. 0 squared is still 0, so we just got to find out what makes x minus 3 0, and that's going to be 3. So our x-intercepts are going to occur at 0 and at 3. For our y-intercept, remember, because this is a function, it has to pass the vertical line test. We've already got 1 point at 0, 0. Our y-intercept is also going to occur at 0. F of 0 is actually equal to 0. That's also our y-intercept. Part B says use the intercepts to find the intervals on which the graph is above or below the x-axis. So here's how we're going to do this. We have zeros at 0 and at 3. So I'm going to plot these points. Here's one at 0, 1, 2, 3, 4, 5, and at 3. What's the degree of this polynomial? 3. The degree of the polynomial is equal to 3 because you have x times an x squared. So are my endpoints going to be pointing in the same direction or in the opposite direction? Opposite direction. The degree is equal to 3, so our endpoints are going to be going opposite directions. Is it going to be increasing or decreasing? Increasing because the leading coefficient is positive, so it's going to have this shape. The multiplicity at 0 is 1, so is the graph going to cross or touch at 0? The 1 is odd, and that means that this is going to cross. So the multiplicity then of the second root at x equals 3 is what? And that is even. So this is going to cross or touch. So the graph then has to have this shape where we are increasing, we cross at 0, come down and touch right there. That's not perfect, but it's close, just based on what we know right now. We can make our graph more refined by doing what? Plot more points, find more points. This is just a big old game of connect the dots. We just got to come up with the dots. I only came up with 2 dots at this point, 2 points that happen to be x-intercepts. So I can refine this, but I do have enough information to answer the question in B. It said use the intercepts to find the intervals on which the graph is above the x-axis and below the x-axis. So to answer this question now based on the graph that I've just sketched out, by knowing the multiplicity of the roots, I can answer this. This graph will be positive on the intervals from 0 to 3, union 3 to infinity. Now this is interval notation. If you don't remember interval notation, I need to know. Remember, when we don't include a point, we use parentheses. When we include a point, we put a bracket. We're not including this point at 3 because it's not actually, the graph isn't above the x-axis, it's on the x-axis at x equals 3. And this graph will be below the x-axis on the interval that goes from negative infinity to 0. This is actually a piece of the number line. It goes from smallest to largest. So if I were to divide the number line right here and right here, this is below, above, and above. But this is your number line. This represents a number line. So this is going from negative infinity out to positive infinity on the right. So that's why I have to write my intervals as such. At this point, we're actually on the x-axis, so right there at x equals 3, I can't include that point. So the union is how we connect those 2 intervals. Part C says locate other points on the graph and connect all the points plotted with a smooth continuous curve. Well, I could do that by plotting more points. So I could take a point in this interval. I could look at f of negative 2. What is f? Let's not use negative 2. Let's use negative 1. Go back to your function, and we plug in a negative 1 here. Negative 1 minus 3 is negative 4, and negative 4 squared is, and 16 times negative 1 is negative 16. So this point right here would have to be at negative 1, negative 16. So I got to put a point way down here just to refine my curve. While I'm at it, I might as well find a point, let's say f of 1. plug in a 1 in place of x. 1 minus 3 is -2. -2 squared is, and 4 times 1 is 4. So we have a point right here that we're going to call 1, 4. Well, that's going to be a fourth of that distance, and so forth and so on. So we can get our shape fairly accurate now just by plotting a few points. We know this is going to take off. And I should actually find another point in this interval. We could try f of 4. 4 minus 3 is, and 1 times 4 is. So we have our other point right here. Just pick points. Plug in the number for x, solve for y. And you can do a lot with graphing now that you probably didn't think about doing in college algebra. Now the next thing we want to look at is the behavior of a function near 0. And this is kind of different. I had never seen this actually until I worked out of this book. And it's kind of cool. It's an interesting way to get how steep this curve is going to be right here at this point. Okay, so what we can do is we can take our values of x, plug them into the function, and get out a y value, and then plot those points as we get closer and closer to x. A nice algebraic way to do this is to come up with a similar function. Instead of plotting all these points, we can actually come up with a similar function by doing the following. For example, we know that if the 0 is a multiplicity that's odd, the graph is going to cross the x-axis. But the question then is, how steep does it cross the x-axis? We know it's a linear function, but how steep is it? Or if it touches the x-axis because that 0 is even, how steep is this quadratic that we're going to end up with? Well, this is a method we can use to answer that question, and you will be asked to do this on your homework. So let's go through an example of how this would look. So for example, suppose we have f of x equals x plus 4 times x plus 2 times x minus 3. Let's consider the behavior near x equals -4. Well, we know that this is going to give us a 0, and this is going to be a linear function, but the question is, how steep is that linear function? Is it increasing or decreasing? Is the constant going to be positive or negative? Well, what we would do is we would plug in a -4 into these other factors. So what we would have is f of x equals x plus 4 times -4 plus 2 times -4 minus 3. Well, -4 plus 2 is -2, and -4 minus 3 is -7. So what we end up with is, near this 0, our graph would have the behavior of f of x equals 14 times x plus 4, near x equals -4. So that tells us that this is a linear function with a very steep x-intercept. So what we would have is we would have a graph that would be almost vertical right there at -4. Our graph would be almost vertical passing through there, crossing through there, because it's 14 is a steep slope. Because this -4 right here came from this factor right there. So I don't plug in the 0 into the factor. That factor became my factor right here. I was trying to get the constant that went with that factor. If I wanted to find the behavior near x equals 3, what two factors would I plug the 3 into in place of x? X plus 4 and x plus 2. We're almost done. It says the multiplicity of a real 0 determines whether the graph crosses or touches the x-axis. The behavior tells you how steep it crosses or touches. We know it's going to be a quadratic, but is it going to be really, really steep or really, really narrow? And that kind of helps us when we do curve sketching without actually plotting points. Now, turning points are the next thing we need to talk about, and the turning points are just exactly what they sound like. It's going to be where the graph turns. So here's a turning point where the graph goes from increasing to decreasing. A turning point will be where this graph switches from increasing to decreasing. So there's a total of 2 turning points. There would be 2 turning points here. Looking at the end behavior here of these endpoints right here and right here, would this power for this function have to be even or odd? Odd. So what we see is, if we have an odd power, our turning points is going to be an even number. As a matter of fact, we have a theorem that says that if we have a polynomial of degree n, then there can be at most n minus 1 turning points. Okay, so if we have a 5th degree polynomial, there can be at most 4 turning points. So identify the graph of the polynomial, and then let's look at the turning points. So which of the graphs in the figure could be the graph of a polynomial function? For those that could, list the zeros and state the least degree the polynomial can have. For those who cannot, say why not. Is this in A a polynomial function? No, it's not. Why is it not a polynomial function? Has a gap. Is this a polynomial function? How many turning points are there? So what is the degree, the maximum degree going to be? 3. Minimum degree. Is this a polynomial function? Why not? Has a corner. Is this a polynomial function? Yes, it is. And what is the degree going to be here? How many turning points? There's 1, 2, 3 turning points, so the minimum degree would be 4. Would the leading coefficient be positive or negative? Negative, because it's pointing down. What about here on this one? Would this be a leading coefficient that's positive or negative? Negative, because this is a decreasing function. It's moving down as you look from left to right. Okay, so we know a lot of information now about the end behavior, and this is where we're going to leave with the summary. We've already gone over a lot of this information. Let's look at this right fast, how to analyze the graph of a polynomial function. If this is our function, first of all, how many zeros are there? What would our x-intercepts be? We have zeros at x equals -1/2 and x equals +3. What is the multiplicity of this 0? Is the graph going to cross or touch here? What is the multiplicity of this graph? Is it going to cross or touch? What about our y-intercept? Do we know our y-intercept here? Our y-intercept is going to occur at 0, so it's f of 0. And that's going to be 2 times 0 plus 1 times 0 minus 3 squared, and that's going to be 9. So we know we have a y-intercept at 0, 9. So already I can sketch in the graph of this function fairly decent using these points. So I have a graph. X is -1/2, so there's 1, 2, 3, 4, 1, 2, 3, 4. So I know that I have x-intercepts at -1/2, 0. That's going to cross there. I have a y-intercept at 0, 9. I have another x-intercept at 3, 0. And I know that the graph is going to be increasing or decreasing? Increasing, because the leading coefficient's positive. This is a 3rd degree, right? So it's going to turn twice. We have a graph that's going up here, touches here, and goes back. The zeros, I found them by setting each one of these factors equal to 0. Let me do that right fast. So I solve, 2x plus 1 equals 0, and that's where I get the -1/2, so I subtract 1 from both sides. That's the one usually that trips people up. So I end up with x equals -1/2, and then from setting that factor equal to 0. All right, that's it.